So 22C is theoretical probability. We are going to do both the notes for C1 and C2 today, and so the first part's C1, and then when it switches to C2, I didn't write it on there, so I'll just kind of give you guys a heads up when we switch to C2. I would say that this stuff, theoretical probability, is pretty basic, but I don't know when the last time you guys did probability was. Probably when you took Algebra 1. Hopefully you did it when you took Algebra 1. So since it's been a while, we will review it. You can go ahead and mark your stat box. Are we good? Okay. So it's sometimes called mathematical probability. I usually prefer the term theoretical probability. It's what we would expect to occur. It is the chance of the event occurring in any trial of an experiment. I know we defined this on Thursday as being probability based on symmetry. So this is like what you would think would happen without like any other factors, without actually doing an experiment, like what you would think would happen. So when we flip a coin, we expect it to land on heads half the time and on tails half the time. That doesn't always happen, but the fact that we expect it to be like half and half, that's the theoretical probability. Like in theory, we would get heads half the time and we would get tails half the time. So in general, theoretical probability is the ratio of the total possibilities of an event happening over the total number of possible outcomes. The possible outcomes are the sample space that we talked about on Friday. So when we have this ratio written out mathematically, so remember this capital P is probability. In this case, A is just representing an event. Like it's a variable, so we don't know what the event is, what's going on, but A just represents an event. So the number of times, the number of members of the event A, so it's like the number of times that that thing could happen, over the total number of possible outcomes, or like the total amount of options over your sample space. So remember that capital U stood for that universal set U. So here we have the number of times that event could happen over the number of possible events that could happen. So like when we roll a die, like a regular six-sided die that you could get like in Monopoly or whatever, how many different things could happen? Six different things. So that's the sample space. There are 6 things that can happen when we roll a die. And let's say the event is rolling an even number. How many even numbers are on your die? 3, because I've got 2, 4, and 6. So there are 3 even numbers, so there's 3 options for that event to happen over the total number of options. So my probability would be 1/2 or 0.5. Does that make sense with like a little example with that? Now, we talked about this on Thursday as well, but remember that your probability is going to be between 0 and 1. Could equal 0 or equal 1, but generally it's in between those two. So our answer of 1/2 makes sense here as well. Any questions? So that some people have gotten some stuff down. I should really write this the probability of even, to keep my notation. So one of the things we need to talk about are complementary events. So two events are complementary if exactly one of the events must occur. So for example, when you flip a coin, it has to be heads or tails. So that's complementary. So if we go back to rolling an even number, if the event is rolling an even number, the complementary event is rolling an odd number because it has to be odd or even. Like together, they are all the possibilities. So again, this is out of your textbook, but this A apostrophe is the notation for the complementary event. So another way to say it is to say not A or whatever it is. So what's the possibility I roll an even number? Well, the complement would be, what's the possibility I do not roll an even number? So it's that other half of that. Together, complementary events will add up to equal 1 because there's a 100% chance one of the two things would happen. And this last little note I added after someone said this out loud in second hour. So the complement is all the other possibilities that are not your original event. I should have put a complement example on the next example. I didn't, but maybe we should make one up. We can make one up. So here we are with our example. And we've got a dish of M&Ms. Does anyone have candy dishes at like their relative's house or anything? Grandma has that candy dish out. All right. So you randomly select an M&M from a dish containing 4 green, 2 blue, 1 brown, 6 yellow, 5 red, and 2 orange M&Ms. Determine the probability of, we've got a few different questions here, and I'm going to squeeze in a question about complements as well. Before we can really start, we need to figure out the sample space, like how many different things that could happen. And I know this is a little bit different than like rolling a die or flipping a coin, but the total number of things that could happen are the total number of M&Ms in that jar, because there are, so many different ones that I could pick up. So those are all the different things that could happen. So how many M&Ms do I have? Got 20. So remember when we do our probabilities, how many times that event could happen over the total number of things. So 20 goes in our denominator, but how many blue M&Ms do we have? So there are two different options for getting a blue M&M. So that's like how many times that event could happen. Now you always want to simplify, or you can give your answer as a decimal. Like when you are checking the back of the book, even in the same section, the answers to 2 might be in a fraction and the answers to 3 might be in a decimal, so you should be able to understand how to get both answers just for checking. I don't really care. So always reduce those, so I'd have 1/10 or 0.1. And I keep forgetting to write the notation, so the probability that I have a blue one. Now, here's where I'm going to squeeze in that complement question. So the complement question would be, like, what's the probability that it's not blue? So you could add up all of the other ones, or again, you could realize that they're going to add up to be 10 or add up to be 20. So if we add up all the other ones, there are 18 M&Ms that are not blue. So that would be, 18 over 20, which would be 9/10 or 0.9. So this is the complement. Does that make sense? Does that kind of make that clear? Like the complement is everything else. All the M&Ms that are not blue is the complement to the M&Ms that are blue. So then we have another event here. A yellow M&M or a green one. We are still over 20 because there are 20 possible M&Ms, but now we're going to have to add the yellow and the green up together. So 4 plus 6 is 10. So 4 green and 6 yellow. So I have 10 out of 20, which should be 1/2 or 0.5. Does that make sense when sometimes we have to add different things together? Okay, what's the probability that I pull a purple M&M?
0.
Yeah, there are no purple M&Ms. This is that impossible event. This isn't some special, Easter version of M&Ms. They're just the traditional ones. So there's just a 0% chance that's impossible. Like I said, I know this is pretty basic, but when do you guys remember the last time you did this kind of stuff? Like we talk about probability in geometry for one day, and it's geometric probability, so it's a little bit different because it has to do with areas, like a target type stuff. But again, I figure since it's been a while, it's not bad to get a little refresher here, even though it's pretty basic. So the next bit of notes would be technically C.2 if you are wanting to, put that in your notes. We're kind of switching from C1 to C2 right here. So the only difference with C2 is that we're going to use 2-dimensional grids to help us find probability. Now, if you were gone on Friday, the 2-dimensional grid is probably going to look kind of crazy to you. What I appreciate about the 2-dimensional grid is it's a nice visual of like what's going on. We're just going to jump right into an example when you guys are done writing this down. The 2D grid we're going to make is kind of small, but there is a larger one in your book. So if you want another example of what it looks like to use a 2D grid, the example in your book is pretty good as well. So we're going to first draw the grid of the sample space. And what we're doing is we're going to flip 2 coins at the same time, a nickel and a dime. And then we'll determine these probabilities using our 2-dimensional grid. So like I said, our grid's going to be kind of small, but it'll still work out. So when we do our two-dimensional grid, remember it almost looks like an x-axis and a y-axis, like branching off. And let's say we've got our nickel, and so our nickel could be heads or it could be tails. Let's say this is our dime, and that again could be heads or could be tails. Does it really matter which one's nickel and which one's dime? Not really. So then we put a dot, where every option. So I could get heads and then heads. I could get tails and then heads. I could get heads and then tails. I could get tails and then tails. So every dot represents a different possible outcome. So we can very clearly see that we have 4 dots. So that's our total sample space. So to get 2 tails, there's only one situation where I can get 2 tails. So I would have 1 over 4 or 0.25. So we can visually see that. Now when you're on your assignment, I don't know if you might want to use different colors or use a pencil because I like to kind of erase. So now at least 1 tail, well, if I go heads and tails, I have 1 tail. If I go tails and heads, I have 1 tail. Tails and tails, it's at least 1. So 2 tails would give me at least 1. So I would have 3 over 4, which would be 0.75 for my fraction. I know it's probably I don't know if it's seeming worth it, but with some of your more complicated ones, with if you're rolling 2 die and you have a 6x6 grid, I do think it helps to circle and see those number of options. So then here we go. If we want exactly 1 tail, well, heads and tails give me exactly 1 tail. Tail and heads give me exactly 1 tail. So that one is just 2/4. So I would have to say 1/2 or 0.5. So again, just that visual representation can help us figure this out. Are there any concerns about calculating the probability? Did I go too fast? Okay. So, in your own words, how do you determine probability? I should have typed in your own words. Especially if you can transfer some of the mathematical stuff into words that make sense to you, I think that will help you remember it. What are the chances? So how do you figure that out? How do you figure out what are the chances? When I teach my little ones, my freshmen, I always tell them in the numerator, it's what you want. You want 2 blue M&Ms. That's what you want. That's what you're looking for. So that goes in the numerator. And the denominator is the total possibilities. So I always say what you want over the total possibilities. Because I also think about when you're playing a board game, sometimes you want a certain role, right? I don't know. That's kind of why I use those words. Those words make sense to me. And here, remember, all the notes were put together for both sections, so we've got the assignments for both parts. There is quite a bit of time, about 20 minutes left, so a couple of things in those 20 minutes. If you have questions on any of your previous assignments, please ask them. You will have a quiz this week, so don't blow off your assignments. Do your assignments, keep current, and keep updated with your work. You will have a quiz this week. And if you need to make up a Chapter 20 or a Chapter 21 test, that needs to happen. Well, Chapter 20 needs to happen this week. 21, we've got another 2 weeks. But if you want to get those, if you need to go over corrections, it would be a really good time for that as well.